Chapter 4, Part 3 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Norman Elfer. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 4, Part 3. Spins. A spin may be defined as an aggravated stall that results in what is termed autorotation, wherein the airplane follows a downward corkscrew path. As the airplane rotates around a vertical axis, the rising wing is less stalled than the descending wing, creating a rolling, yawing, and pitching motion. The airplane is basically being forced downward by gravity, rolling, yawing, and pitching in a spiral path. Figure 4-9. The autorotation results from an unequal angle of attack on the airplane's wings. The rising wing has a decreasing angle of attack, where the relative lift increases and the drag decreases. In effect, this wing is less stalled. Meanwhile, the descending wing has an increasing angle of attack, past the wing's critical angle of attack, stall, where the relative lift decreases and drag increases. A spin is caused when the airplane's wing exceeds its critical angle of attack, stall, with a side slip or yaw acting on the airplane at or beyond the actual stall. During this uncoordinated maneuver, a pilot may not be aware that a critical angle of attack has been exceeded until the airplane yaws out of control toward the lowering wing. If stall recovery is not initiated immediately, the airplane may enter a spin. If this stall occurs while the airplane is in a slipping or skidding turn, this can result in a spin entry and rotation in the direction that the rudder is being applied, regardless of which wingtip is raised. Many airplanes have to be forced to spin and require considerable judgment and technique to get the spin started. These same airplanes that have to be forced to spin may be accidentally put into a spin by mishandling the controls in turns, stalls, and flight at minimum controllable airspeeds. This fact is additional evidence of the necessity for the practice of stalls until the ability to recognize and recover from them is developed. Often, a wing will drop at the beginning of a stall. When this happens, the nose will attempt to move, yaw, in the direction of the low wing. This is where use of the rudder is important during a stall. The correct amount of opposite rudder must be applied to keep the nose from yawing toward the low wing. By maintaining directional control and not allowing the nose to yaw toward the low wing before stall recovery is initiated, a spin will be averted. If the nose is allowed to yaw during the stall, the airplane will begin to slip in the direction of the lowered wing and will enter a spin. An airplane must be stalled in order to enter a spin. Therefore, continued practice in stalls will help the pilot develop a more instinctive and prompt reaction to recognizing an approaching spin. It is essential to learn to apply immediate corrective action anytime it is apparent that the airplane is nearing spin conditions. If it is impossible to avoid a spin, the pilot should immediately execute spin recovery procedures. Spin procedures. The flight instructor should demonstrate spins in those airplanes that are approved for spins. Special spin procedures or techniques required for a particular airplane are not presented here. Before beginning any spin operations, the following items should be reviewed: the airplane's AFM/POH limitations section, placards, or type certification data to determine if the airplane is approved for spins. Weight and balance limitations. Recommended entry and recovery procedures. The requirements for parachutes. It would be appropriate to review a current Title 14 of the Code of Federal Regulations, 14 CFR, Part 91, for the latest parachute requirements. A thorough airplane pre-flight should be accomplished with special emphasis on excess or loose items that may affect the weight, center of gravity, and controllability of the airplane. Slack or loose control cables, particularly rudder and elevator, could prevent full anti-spin control deflections and delay or preclude recovery in some airplanes. Prior to beginning spin training, the flight area above and below the airplane must be clear of other air traffic. This may be accomplished while slowing the airplane for the spin entry. All spin training should be initiated at an altitude high enough for a completed recovery at or above 1,500 feet AGL. It may be appropriate to introduce spin training by first practicing both power on and power off stalls in a clean configuration. This practice would be used to familiarize the student with the airplane's specific stall and recovery characteristics. Care should be taken with handling of the power, throttle, in entries and during spins. Carburetor heat should be applied according to the manufacturer's recommendations. There are 4 phases of a spin: entry, incipient, developed, and recovery. Figure 4-10. Entry phase. The entry phase is where the pilot provides the necessary elements for the spin, either accidentally or intentionally. The entry procedure for demonstrating a spin is similar to a power-off stall. During the entry, the power should be reduced slowly to idle, while simultaneously raising the nose to a pitch attitude that will ensure a stall. As the airplane approaches a stall, smoothly apply full rudder in the direction of the desired spin rotation, while applying full back up elevator to the limit of travel. Always maintain the ailerons in the neutral position during the spin, unless AFM/POH specifies otherwise. Incipient phase. The incipient phase is from the time the airplane stalls and rotation starts until the spin has fully developed. This change may take up to 2 turns for most airplanes. Incipient spins that are not allowed to develop into a steady-state spin are the most commonly used in the introduction to spin training and recovery techniques. In this phase, the aerodynamic and inertial forces have not achieved a balance. As the incipient spin develops, the indicated airspeed should be near or below stall airspeed, and the turn and slip indicator should indicate the direction of the spin. The incipient spin recovery procedure should be commenced prior to the completion of 360 degrees of rotation. The pilot should apply full rudder opposite to the direction of rotation. If the pilot is not sure of the direction of the spin, check the turn and slip indicator. It will show a deflection in the direction of rotation. Developed phase. The developed phase occurs when the airplane's angular rotation rate, airspeed, and vertical speed are stabilized while in a flight path that is nearly vertical. This is where airplane aerodynamic forces and inertial forces are in balance, and the attitude, angles, and self-sustaining motions about the vertical axis are constant or repetitive. The spin is in equilibrium. Recovery phase. The recovery phase occurs when the angle of attack of the wings decreases below the critical angle of attack and autorotation slows. Then the nose steepens and autorotation stops. This phase may last for a quarter of a turn to several turns. To recover, control inputs are initiated to disrupt the spin equilibrium by stopping the rotation and stall. To accomplish spin recovery, the manufacturer's recommended procedures should be followed. In the absence of the manufacturer's recommended spin recovery procedures and techniques, the following spin recovery procedures are recommended. Step 1. Reduce the power, throttle to idle. Power aggravates the spin characteristics. It usually results in a flatter spin attitude and increased rotation rates. Step 2. Position the ailerons to neutral. Ailerons may have an adverse effect on spin recovery. Aileron control in the direction of the spin may speed up the rate of rotation and delay the recovery. Aileron control opposite the direction of the spin may cause the down aileron to move the wing deeper into the stall and aggravate the situation. The best procedure is to ensure that the ailerons are neutral. Step 3. Apply full opposite rudder against the rotation. Make sure that full, against the stop, opposite rudder has been applied. Step 4. Apply a positive and brisk, straightforward movement of the elevator control forward of the neutral to break the stall. This should be done immediately after full rudder application. The forceful movement of the elevator will decrease the excessive angle of attack and break the stall. The controls should be held firmly in this position. When the stall is broken, the spinning will stop. Step 5. After spin rotation stops, neutralize the rudder. If the rudder is not neutralized at this time, the ensuing increased airspeed acting upon a deflected rudder will cause a yawing or skidding effect. Slow and overly cautious control movements during spin recovery must be avoided. In certain cases, it has been found that such movements result in the airplane continuing to spin indefinitely, even with anti-spin inputs. A brisk and positive technique, on the other hand, results in a more positive spin recovery. Step 6. Begin applying back elevator pressure to raise the nose to level flight. Caution must be used not to apply excessive back elevator pressure after the rotation stops. Excessive back elevator pressure can cause a secondary stall and result in another spin. Care should be taken not to exceed the G-load limits and airspeed limitations during recovery. If the flaps and/or retractable landing gear are extended prior to the spin, they should be retracted as soon as possible after spin entry. It is important to remember that the above spin recovery procedures and techniques are recommended for use only in the absence of the manufacturer's procedures. Before any pilot attempts to begin spin training, the pilot must be familiar with the procedures provided by the manufacturer for spin recovery. The most common problems in spin recovery include pilot confusion as to the direction of spin rotation and whether the maneuver is a spin versus spiral. If airspeed is increasing, the airplane is no longer in a spin but in a spiral. In a spin, the airplane is stalled. The indicated airspeed, therefore, should reflect stall speeds. Intentional spins. The intentional spinning of an airplane, for which the spin maneuver is not specifically approved, is not authorized by this handbook or by the Code of Federal Regulations. The official sources for determining if the spin maneuver is approved or not approved for a specific airplane are type certification data sheets or the aircraft specifications. The limitations section of the FAA-approved AFM/POH. The limitations sections may provide additional specific requirements for spin authorization, such as limiting gross weight, CG range, and amount of fuel. On a placard located in clear view of the pilot and the airplane, no acrobatic maneuvers including spins approved. In airplanes placarded against spins, there is no assurance that recovery from a fully developed spin is possible. There are occurrences involving airplanes wherein spin restrictions are intentionally ignored by some pilots. Despite the installation of placards prohibiting intentional spins in these airplanes, a number of pilots and some flight instructors attempt to justify the maneuver, rationalizing that the spin restriction results merely because of a technicality in the airworthiness standards. Some pilots reason that the airplane was spin tested during its certification process and therefore no problem should result from demonstrating or practicing spins. However, these pilots overlook the fact that a normal category airplane certification only requires the airplane recover from a one-turn spin and not more than one additional turn or 3 seconds, whichever takes longer. This same test of controllability can be used in certificating an airplane in the utility category, 14 CFR Section 23.221b. The point is that 360 degrees of rotation, one-turn spin, does not provide a stabilized spin. If the airplane's controllability has not been explored by the engineering test pilot beyond the certification requirements, prolonged spins, inadvertent or intentional in that airplane, place an operating pilot in an unexplored flight situation. Recovery may be difficult or impossible. In 14 CFR Part 23, Airworthiness Standards, normal, utility, acrobatic, and commuter category airplanes, there are no requirements for investigation of controllability in a true spinning condition for the normal category airplanes. The one-turn margin of safety is essentially a check of the airplane's controllability in a delayed recovery from a stall. Therefore, in airplanes placarded against spins, there is absolutely no assurance whatever that recovery from a fully developed spin is possible under any circumstances. The pilot of an airplane placarded against intentional spins should assume that the airplane may well become uncontrollable in a spin. Weight and balance requirements. With each airplane that is approved for spinning, the weight and balance requirements are important for safe performance and recovery from the spin maneuver. Pilots must be aware that just minor weight or balance changes can affect the airplane's spin recovery characteristics. Such changes can either alter or enhance the spin maneuver and/or recovery characteristics. For example, the addition of weight in the aft baggage compartment or additional fuel may still permit the airplane to be operated within CG, but could seriously affect the spin and recovery characteristics. An airplane that may be difficult to spin intentionally in the utility category, restricted aft CG, and reduced weight could have less resistance to spin entry in the normal category, less restricted aft CG, and increased weight. The situation is due to the airplane being able to generate a higher angle of attack and load factor. Furthermore, an airplane that is approved for spins in the utility category, but loaded in the normal category, may not recover from a spin that is allowed to progress beyond the incipient phase. Common errors in the performance of intentional spins are failure to apply full rudder pressure in the desired spin direction during spin entry, failure to apply and maintain full up elevator pressure during spin entry, resulting in a spiral, failure to achieve a fully stalled condition prior to spin entry, failure to apply full rudder against the spin during recovery, failure to apply sufficient forward elevator pressure during recovery, failure to neutralize the rudder during recovery after rotation stops, resulting in a possible secondary spin, slow and overly cautious control movements during recovery, excessive back elevator pressure after rotation stops, resulting in possible secondary stall, insufficient back elevator pressure during recovery, resulting in excessive airspeed. End of Chapter 4.